In this video, we will solve example 5.3 from the book McConkey and Td Eastop. So what's the statement say? Let's begin. In a gas turbine unit, air is drawn at 1.02 bar and 15 centigrade. So the air is supplied at this point to the compressor at a pressure is 1.02 bar and temperature is 15 centigrade. So if I draw that on a TS diagram, at the point 1, so the temperature will give you 288 if I convert into Kelvin, and the supplied pressure is uh, 1.02 bar. So this is a constant pressure line. So the pressure at point P1 and P4 will be the same, and similarly the pressure at point P2 and P3 will be the same. So next it is compressed to 6.12 bar. So the purpose of compressor is to increase the pressures of the fluid. So between 1.1 to 2 there is a compressor installed, so the pressure increased from 0.1 to 2 up to 6.112 bar. So this is a constant pressure line. So the pressures at point P2 is the same as P3. Now to calculate the thermal efficiency and the work ratio of the ideal constant pressure cycle. So we have to calculate the thermal efficiency and the work ratio of this cycle when the maximum cycle temperature is limited to 800 centigrade. So the maximum cycle temperature is obtained at a T3. Why at a T3? Because heat is supplied continuously at a constant pressure. So that's why here the heat is supplying. So the heat is supplying, that's why the maximum temperature is obtained at a point T3. So if you convert that into Kelvin, it becomes 1073 Kelvin. Now let's begin the problem. What it says, we saw that temperature T1 uh, that is given the lowest temperature here, it is that is 288 Kelvin. So that is already converted into Kelvin. Now conversion to Kelvin is very easy, and the maximum temperature, that is T3 here, this is T3, that is 800 centigrade. So when convert that into Kelvin, just add 273 with it, so you will get 1073 Kelvin. Okay. Next is the pressures. So the pressure P1, and you know that this is a constant pressure line, so the pressure at P1 is the same as P4, that is 1.02 bar, and the pressure P2 is the same as P3. P2 is equal to P3, and that is 6.112 bar. Okay. These are the constant pressure line. Also, you know that the gas turbine always work on a Brayton cycle, that is also called constant pressure cycle, that uh, contain two isentropic processes and two constant pressure processes. Okay. Next we have to find the thermal efficiency of this cycle and the work ratio of this cycle. Okay, let's begin its solution. These are just the understanding what the example 5.3 actually says. Now come towards its solution. Now the solution is very simple once you understand all the statement and the concept that what I have explained so far. Thermal efficiency is equal to 1 minus 1 divided by Rp. Rp is nothing but this is a pressure ratio. 1 gamma minus 1 divided by gamma. Remember, this is in the power form, not in the base form. Okay. So what is Rp? Rp is the pressure ratio. So higher pressure ratio to lower pressure ratio. That means P2 divided by P1, or So this P2 is equal to P3, so you can write P3 and also P4. So that is equal to, what is P2? That is 6.12 divided by 1.02. So it will become equal to 6 bar if you solve this by using the calculator. Now the thermal efficiency is quite simple to calculate, because the pressure ratio we have calculated. Just enter the values, where the corresponding values of the corresponding um, unknowns that we have calculated for 1, and you also know the value of gamma is 1.4, so the P value is 6, gamma is 0.4. Here it becomes, when you subtract, gamma value is 1.4, so when you subtract 1 from it, it becomes 0.4 divided by 1.4. So after doing the calculations, we will get the efficiency of this term of this cycle is. Let me do the calculations. So after using the calculator, when you use the calculator, using the calculator, I think you already familiar with that. You will get its efficiency, that is 40%. Next is, before finding the work ratio, you must be familiar how much work output is obtained during this turbine isentropic expansions. When there is isentropic expansions occur from point 3 to 4, with the help of this turbine, it will deliver you some work output. So that's work out you have to calculate before going to calculate the work ratio. Output by the turbine is the Cp, so the temperature, the maximum temperature T3, and the temperatures at the exit of the turbine, that is T4. So the T3 is known, that is 1073 Kelvin, and T4 is unknown. So before going to put that in this equation, to find the work done to T4 should be calculated. Okay, so this is isentropic expansion. So apply the, so the temperatures is already known between the higher pressures and the lower pressures of the cycle. So apply the isentropic equations of the pressures and temperatures to find this T4. So T3 divided by T4 is equal to P3 divided by P4 into gamma minus 1 divided by gamma. Okay, so this T3 is divided by T4 is equal to, what is P3 by P4? That is simple, 6 into gamma. Gamma is 1.4, so when you subtract 1 from it, it becomes 0.4 divided by gamma, that is 1.4. So this, after using the calculator, you will get its value is 1.669. I'm getting round about it. So now things are getting very easy. So T3 is known, that is 1073 Kelvin, and if you shift that T4, it will be in the product form, that is 1.669. So if you divide both sides with 1.66, you will get the T4 value, that is 642.9 Kelvin. So the T4 value is 642.9 Kelvin after uh, doing simplifications and doing calculation by using calculators. So you'll get the T4 value like 642.9 Kelvin. Now put that in this equations to find the work output of the turbine that is delivered to you. Cp is 1.004, Then what is T3? T3 is 1073 minus what is T4, that is 642.9. So after that work output you will get. After using calculator, I think using the calculator is very easy. I suppose that you are familiar with that, so that's why I'm not doing the calculations, because if I doing the calculations the video will become lengthy and student gets very bored. So that's why, to keep the video short, I skip the calculation portion, because the calculations of the exam is 5.3 is very easy. So I'm writing directly the final values of each strip. For 32.2 kilojoule per kg, the work output you have to obtain by doing the isentropic expansions in the turbine. Next, we have to find the work that is supplied to the compressor to run the compressors. So we have to supply that work, so that we denote it by WC. So the work that is required to run the compressors is calculated from one temperature T2 to T1. The temperature T2 is unknown in this case, but the temperature T1 is known, so that is Cp into T2 minus T1. So again we have to calculate the T2 in this case, or apply the isentropic process from process 1 to 2. So that is T2 divided by T1 is equal to P2 divided by P1 into gamma minus 1 divided by gamma. So by putting the values of P2, P1 and gamma minus 1 divided by gamma, so you will get this value. So I already write that details. So I am directly writing its value. So that is T2 divided by T1 is equal to 1.669. So the T1 value is known, that is 288. So the T2 value will be 1.669 multiplied by 288 to find. So the final value of T2 will be, after multiplying it, 166 for 80.5 Kelvin. Now put that value in this equations of the compressors, work done to the compressors in order to run that. 1.004 into 480.5 minus T1, that is 288. So the work output of the compressor is equal to, so the work that is required to run the compressor is 193.46 kilojoule per kg. Remember, we are interested to find the value of work ratio. So here is our main concern is to find the value of work ratio. We are about to near uh, its calculation. So the net work that we obtain during this work, this cycle expansion, this complete cycle. So the net work that we obtain during this cycle completions is So the work that is delivered by the turbine and the work that is supplied to the compressors will give you the net work output. So the work done by the turbine is 4, so here it is 432.2, and work supplied to the compressor is 193.46. So after doing the calculations, you will get its value. The net work output is 238.8, around about kilojoule per kg. The next is the gross work. Gross work means the work that you obtain, that is, you can say, the work output of the turbine, that is 432.3 kilojoule per kg. So now, to find the work ratio, so all the things has been calculated for the work ratio. Is the net work output. So this is the network output, and here its final value. Just put that here, and the work output of the turbine, we call it the gross work also, that is the gross work or work output of the turbine. So by putting its value, so the at the top you will get 238.31, and the denominator, the work output of the turbine, is 432.3. By solving it on calculator, you will get 6. The work ratio is 0.533. So 10 is 0.553. Okay. Thank you so much for watching for solving the example 5.3. More problems and example solutions are on the way. Subscribe my channel.